Okay. So, this has been up on the board. I do want to move on. That's why I'm going to go through this. I'm going to give you guys a moment. I gave you more than 2 minutes. I've given you at least 5 now, Evan. Okay, so this question, let's just have a go through the parts of it. So part A, we just wanted to show that if f of x is equal to x cubed minus 3x, we wanted to show that f dash is equal to 3x minus 1, x plus 1, and f double dash is equal to 6x. So, my original function f of x is equal to x cubed minus 3x. How do I get f dash x? What do I need to do? I need to differentiate. Excellent. Can someone on this table help me out? What do I get when I differentiate this function? 3x squared. Yeah, excellent. And we want to show that it is equal to this guy. What might we do as a first step to get there? Take 3 out from both of them. So here I'm going to take 3 out from both of them. I get x squared minus 1. Difference of 2 squareds. Thank you, Boyd. And then from there I can factorize x plus 1, x minus 1. In this case, because the question does say x minus 1, I'd probably want to write it as x minus 1 first and then x plus 1 is second. Cool. What's the second step to get to this f double dash? What do I need to do? Differentiate again. Now, out of my two, if you have a look for my first derivative, I've written it in 3 different forms. I've got form 1, 2, 3. Which one do you think is the easiest to differentiate? 1. Easy. Okay, cool. So we're going to differentiate 1, and when we differentiate, what do we end up getting?
3 times 2.
Yep, 6x. Excellent. Which is exactly what we want to prove. There we go.
So do we exactly show it that we're like times ingredients?
If the question says show, like if it's a specific question that says show, you probably want to do like the 2 times 3x is equal to 6x. But if it doesn't say show,
It says show.
Screw it. In an exam, you would, but like in most cases, you don't really need to. Okay, B. By solving f dash x is equal to 0, okay. When you have f dash x is equal to 0, what does that mean for our graph? We have a stationary point. That's our point where the gradient is equal to 0. That's what the first derivative tells us. So let's solve f dash x is equal to 0. F dash x is equal to 0 means that, and we factorize it for a reason. 1 and negative 1. Irvin, how did you get 1 and negative 1? That's the zeros. Excellent. So here, this was the equation that we got from the previous part. We're solving this guy is equal to 0. This guy here, we're solving for that guy is equal to 0. And as Irvin said, those are our 2 zeros. We just solve each one of those factors separately. So x is equal to 1, x is equal to minus 1. Okay. Following step. Part C was we wanted to determine the nature of these stationary points. How do we determine the nature of the stationary points? And we went through 2 different methods of doing this. What's the first method we did? Okay, so there's two methods. So TJ's mentioned you can differentiate again, like we did. We've already found the second derivative, and then we can sub in those values. And that will tell us the concavity at those points. So if the second derivative is negative, is that concave up or down? Down. It's a frowny face. If it's the second derivative is greater than 0, that looks like a bird. If the second derivative is greater than 0, is it concave up or down? Up. So it looks like this. And so if we have a second derivative is less than 0, that point here, is that a local maximum or minimum? Max. And over here, if I have greater than 0, is that a local maximum or minimum? Yeah, so that's one way that we can check. We can sub in our stationary points into the second derivative, and that will tell us if it's a maximum or minimum. What's the other method? Mariam, you were saying something. Yeah, you can draw a table of values. So let's just quickly go through both those methods. So the first, the one that Mariam is suggesting was to draw up a table of values. Now here you could also do the f of x. I'm not going to worry too much about the x values at those points. What do I need to put in my table of values? 1 and negative 1, which one do I, what do I put? Minus 1. Put minus 1 here, 1, and what do I put in between? Dot, dot, dot. Those just represent the values in between. What do I know about the first derivative at those 2 points? It's equal to 0. Those are our stationary points. That's what we found. So from here, what are we trying to do? What do we need to do? we're going to check if the first derivative is positive or negative by subbing in values in the dot dot dots. What's a value I can chuck in for this first set of dot dot dots? -2. If I sub in -2 into my first derivative, what do I get? -2 on my first derivative. Yep, so it's a positive or negative? Positive, excellent. So it's over here, it's positive. In between, what's a value? 0. If I sub in 0 into my first derivative, what do I get? Negative. And on the other side, if I sub in a value here, positive. Cool, so what does that tell me about my graph? I go this up, down, up. So what does this tell us about -1? It is a local what? Maximum, excellent. You look at the shape, we're going up and then down. So that's a local maximum. Down here at 1, local minimum, excellent, because we're going from down to up. So that's one way you can do it. And today, in the example that we're going to do, we're going to actually have a look at the other way that we can do it by using the second derivative. So I'll keep this up here for a second. Can you please turn to page 17 in the booklets, and then we're going to keep moving, hopefully a fairly brisk pace. I'm using my phone for educational purposes. Ooh! If you turn to page 18, there's a link there, and when I put my phone over it, my camera side just detected the URL. I'm so amazed. I'm so amazed. Huh? No. Everyone knows it's XQC at the end. Yeah. No, that's just the first, that's our, what's it called? F of x. Because in the last row, so f of x, because we want to see what the original function looks like. We don't want to see what the second derivative looks like. We want to look at what the original function will look like. So this tells me the shape of the function. Yeah? Cool. Okay. I am going to move back to page 17. Now, last lesson, a few of you away, we went through this example where we identified different parts of our curve.
What page?
I did. I didn't post a link now, did I? Very dumb of me. I'll do that. Okay, page 17. We're going to go through this example on page 17. I'm going to show you how we can actually use the second derivative to tell me what the nature of the stationary points are. So, this is from the 2012 HSC. Question 14. Page 17. Okay, now. Sure. Wait, no. I like it. Fine, turn it off. Hurry up. Okay, here we go. Question. Hey, Evan. Let's go. Okay, a function is given by this particular equation. So we've got f of x is equal to 3x to the power 4 plus 4x to the power 3 minus 12x squared. First part. We want to find the coordinates of the stationary points and determine their nature. How can we find the coordinates of stationary points? What do we do? Huh? What?
X equals to 0.
What?
Yo, you have a cheat sheet all that?
We differentiate. Excellent. The first step that we need to do is we need to differentiate. So let's differentiate this guy. Table at the front here. Can someone help me? What do I get when I differentiate this guy, this function? 12x to the power 3. 24x. Excellent. Now that I've done that, what do I need to do to find stationary points? I've differentiated, now what do I need to do? Huh? We need to let this equal to 0. We need to solve for this equal to 0. So, the way that we can do this, to make it a little bit easier for us, what might be a following step that I can do to my derivative? Factorize. I'm going to take 12x out. Thank you, Ujin. Ujin, what do I get left when I take 12x out? No, Ujin actually said 12x. I heard him. X squared. Thank you. Excellent. Okay, now at this point we want to solve for this guy is equal to 0. I'm actually going to keep factorizing so it makes it easier. And I'm just going to do the solving in a further step. Can I factorize this any further?
Yes.
Yes. What? 2 and minus 1, thank you. 12x, x plus 2, x minus 1. You remember factorizing quadratics? We're looking for two numbers that add together to give me 1 and multiply to give me minus 2. So add to give me 1, multiply to give me minus 2. And this factorizing bit, well, this factorizing bit actually helps me solve for my stationary points a lot quicker. So, for example, here, now that I've done that, where do I know my stationary points are? X is equal to negative 2. 1 is another one. There's one more. 0. Excellent. There's actually 3 factors here. There's 3 factors here. There's this x plus 2, x minus 1, and this x by itself. So here we've got 3 factors. So those are my 3 stationary x values. My stationary points x values. What do I need to do with these values now? Sub into what, Ujin? Excellent. Okay, so Ujin said we need to sub this back into the original one. Why do we need to sub it back into the original one? Excellent. So here, now that we've done that, guys, point. Now that we've done that, we've found us the x values of my stationary points. I need to actually find my y values. So I'm going to sub all of these values back into my original functions. So one of these is probably very easy to do. Which one do you think is the easiest to sub in? 0, because it's just 0. Excellent. Okay, I've got one of my stationary points. Yes, I need to substitute these in. Well, for this stage, when we're subbing it into the original function, notice here this isn't f dash, it is just my original function. I want to find out the exact y values here. So when x is equal to 1, what's the y value going to be? Let's do the one at the bottom.
You have to sub 1 into the first one.
Which will give me negative 5. Negative 5, I believe is correct. Okay, we also need to sub in negative 2. I'm going to trust that you know how to do this and you can check in the calculator out. But so in the table, okay, so if you're the example that I did before, what we did was we subbed in values into f dash that were either side of my zeros to determine the nature. What we're trying to do right now is to figure out the y values that would actually take up these spots here. The local minimum, local maximum. What we're trying to find is the number that would go into these spots here. So, this question that we did before, just to get us started, I didn't bother doing the y values because I'm like, okay, we just want to do a quick example just to guess with the skills. If they ask you to find, so if you have a look at this question, what tells you you need to find the y values of those points? What particular word gives that away? Guys, there's a word that hints that you need to get these y values, and usually you would need to get the y values. Thank you. Coordinates. What do coordinates involve, year 12s? X and a y. So you need 2 values. So this is why I'm doing all of this, putting these values in. Now, did one of you guys put in negative 2? What did you get?
Wait, is it?
Huh? Well, negative 8.
What did I say?
That'd be fine.
I said negative 2. Oh, it's 32. I thought that was 24.
Good Lord. Isn't it minus 32? Minus 32. Okay, cool. So, from these substitutions, what we found is, where's my first stationary point at? Where's my first stationary point at? Minus 2? Minus 32. Where's my second stationary point at? Irvin.
0 and 0.
Excellent. Final stationary point is at
1 and minus
Excellent. So we've found the coordinates of the stationary point. So this first part we've ticked off. What do we need to do as well?
We need a
Determine their nature. Excellent. Now, in the example that we did before, we did the table of values method. The second method that TJ said was we can actually differentiate again, and that will help us by, once we've differentiated again, we can sub in the x values of my stationary points, and it will tell me the concavity at those given points. So let me show you how we do that. So guys, let's differentiate again. So if I differentiate again to get the second derivative, Boyd,
What?
can we stop talking, thank you. Let's differentiate again. What do we get when we differentiate a second time? Let me make this a little bit clearer so we can see it. F dash double dash x. What do I get when I differentiate again?
12 times 3
Which is?
x
Squared?
plus 24x minus 24.
Excellent. Here you can choose to factorize. I think factorizing it does it make a difference? Yeah, it does. Yeah. Yeah. Okay. So this one, notice here in any of the parts. So what does the second derivative tell us? It's the C word was concavity. And in particular, there's like a key feature involved with concavity. Guys. Year 12s. Along with concavity, there's a key feature that's involved with concavity that the second derivative can tell us. It's a 3-letter acronym. Point of inflection. So point of inflection is where
It goes like
it swaps concavity. So we go suddenly from concave up to concave down. So for example, this point here is your point of inflection. It's where it swaps concavity. So we can, if the questions ask you to find the point of inflection, we probably want to factorize it. For this question, when we're trying to just determine the nature, we don't really need to worry about that too much. Okay, now with the second derivative, what we can do is we can sub in all of my stationary points, so all the x values of my stationary points, and I will show you how this actually helps us determining the nature. So what do I get when I have, let's start with 0, because that's the easiest one. When I sub in 0, what do I end up getting? No need, negative 24. Is that positive or negative? Negative, which means it is concave what? Concave down. Excellent. Now, if we link this back to my stationary point, we know that at 0, 0, we have a stationary point, right? So 0, 0 is our stationary point that we got from up here. If it's concave down, so concave down means it's like this, where is the stationary point on my concave down? It's a maximum. Does everyone see that? Concave down, we have a stationary point up here, which is a local maximum. So this actually tells me that this is a local maximum. Okay, let's do this again for the next one. So let's do 1 because 1 is the next easiest one. When I sub in 1 into my second derivative, what do I get? Huh? 36, excellent. It's 36 greater than or less than 0? Greater than, which means it's concave up. Which means that if I bring this back to my stationary point, we had a stationary point at 1, negative 5. Is that a local maximum or minimum? If we draw concave up, it's a local minimum because if you have a look, if I have a concave up section, this happy face, the only stationary point there is this point here. It's a minimum happiness. Minimum happiness. Maximum sadness. Okay, cool. So local minimum, let's do it for the final one, which is negative 2. When I sub in negative 2, what do I get? Huh?
I can't do 36.
Hang on. Shh. You can chuck this in the calculator. Let's just, in the case you're not. 30. Okay, we're going to wait until Irvin does it now. He's provoked me.
No, do it.
Make me open my
Do it.
Yes. You're not guessing, you're thinking. It is 16.
No.
Is it actually 144? You do it?
Come on, Evan.
So, it's your time wasting, not my time.
Yeah.
If you have a calculator, please use it.
It's 16. That was rough on my head.
It's just that.
Positive. So it has to be positive. Come back. Yes, I told you it was right.
It's 72.
Tell me I wasn't right. What?
72, which is?
That's what you said.
Okay, guys. Shh. Back on the board. 72. Is that positive, negative? Which means it's? Which means that at negative 2, it's a local min. Local minimum. Okay, so that's us determining the nature. So here, you can actually, instead of having to draw up a table and testing points either side, you can actually just sub in,
You can just say it's negative or positive.
and then it will tell you if it is a,
That will do.
yeah, exactly right. There we go. Everyone cool with that?
Yeah.
Okay, so we've discovered that we've got these points here, and this actually tells us different values about my graph. Okay, that's part I. Part double I. We need to sketch our graph. Now, so here notice it sketched the graph of y is equal to f of x, showing the stationary points. Showing the stationary points. Now, oh, this is gonna hurt my brain.
What did he say?
I hate this already. Hang on.
So,
Yes.
I think we should have questions that. That's right.
We should just get rid of that.
Oh, this hurts my brain. I hate this. Okay, cool. Never mind. Okay, so part double I. Hence, sketch the graph of y is equal to f of x, showing the stationary points. Now, we found all these stationary points. We can actually use this quite quickly to draw the graph. So, I'm going to draw my Cartesian plane. Y, x. So, where is my first point that I've just found? Negative 2 and negative 32. Now this is not going to be to scale, but I've got negative 2, negative 32. So I'm going to put a dot here just to line up the two. Okay, I've got my first stationary point. What's the next stationary point I have? 0, 0. I've got a stationary point here. Where's my next stationary point? 1, negative 5. So I'm going to have a dot around here. This is 1, and negative 5 is about here. Okay, and so using your stationary points, we can actually draw a graph. The first point is a local minimum, which means that on the left-hand side, we need to go down towards it, and then we go back up.
Down towards it.
Then my second point, 0, 0, is a local minimum or maximum. Maximum, which means it needs to go from the left-hand side up to it, and then go back down. And then 1, negative 5 is a local minimum, which means we need to go down and back up. And there we go. It looks kind of like a weird W. So finding our stationary points like that, we can actually just draw a graph like this. Yes?
Where would be the x intercept?
That's exactly the thing that was hurting my brain. You can find the x-intercepts.
Or
We can ignore it.
we can go home.
In the exam, I would recommend you find the x-intercepts. How do you find x-intercepts? Y is equal to 0, which is just you're solving the original function is equal to 0. So here you would be solving 3x to the power 4 plus 4x cubed minus 12x squared is equal to 0. You can factorize it and it should give you some numbers to put in annoyingly. Okay, cool. So that's part 2. Excellent. Is everyone cool with part 2? You can just plot on your stationary points, identify whether or not they're a local minimum, local maximum, a horizontal point of inflection if necessary, and then just draw the shapes that fit into those points. That's all you need to do. Okay.
How do you get the x intercept?
You solve f of x is equal to 0.
Yeah. Count the point.
Mariam is trying to make us do extra work.
It's period 1.
They solve something you don't know.
Okay, here, then you need to use what formula to help you solve for this guy here?
It's gonna be like some
Quadratic. X is equal to negative 4 plus or minus square root.
one.
Oh, I haven't seen this so long.
4 squared minus 4 times 3 times minus 12 over 6. You asked for it, Marianne.
Yeah.
No, you said it. Oh, Lord.
Oh, it's on that formula sheet.
It's not a moment. It's fine.
It's fine. We'll see it. If you need it.
Yeah, I think it gives you this. Those are the two x-intercepts. Square root 10.
Oh.
I just jumped a few steps here. So here you would need to like do a few factorization steps. You would need to use the quadratic formula, and then you can get some x-intercepts here. Thank you, Marianne, for asking extra questions. Okay, part 3.
I did not know.
So I think no one is left.
Well, congrats.
No one's thinking of
Make space. Part 3. Okay, part 3. Part 3. This one's a very quick one. This is a very quick graph. Quick question.
I don't think I'm going to do
If you have a look at part 3, for what values of x is the function increasing? If you have a look at your graph, how do we know if the function is increasing? If it's going from the first derivative is greater than 0, that's one condition. But just by looking at the graph, it goes up. So which sections are going up? Between where? Greater than negative 2 and all the way to less than 0. So TJs know this. Increasing, this first section is when x is between
increasing 0.
negative 2 and
X
0. That's the first section. What other section is our graph increasing?
That
Greater than 1.
Up.
Yeah. So here, these are the two sections which are increasing because we're going up. If it's going up, we are increasing. To infinity and beyond. Well, in the first section, you're not going to infinity. You're going to between negative 32 and 0. But to infinity and beyond is the next section. Okay, cool. Part 3 was quite easy because you just had to read off the graph. Read off the graph. Read off the graph. Okay, part 4 is the one where it requires you to think. It's 1 mark. And it's also a very simple one if you can figure out what they're actually asking. Originally, I was looking at this going like, I don't understand this question. And I saw the graph and I'm like, I see. Okay, for what values of k will this guy here have no solution? So notice here in the question, yeah. So you're trying to find what you need to put in for k in order for this equation to have no solutions. Now, what does it mean if I was to draw a function? So let's say I drew a function like this and had like negative 1, 2. What are the two solutions of my quadratic here? X is equal to minus 1 and 2. So when you think of it graphically, a solution is when you have x-intercepts. Solutions are your x-intercepts.
Oh, this is like, you gotta move it because thing that we learned where you, if you like add after equation, it moves it upwards.
Yeah. Yeah, excellent. So, TJ's remembered that during graphical transformations, what we can do is we can actually transform graphs by going, it's not dilations, it's a translation. You can move a graph upwards by adding a number at the end. If you have a look at this graph here, what do I need to add in order for the graph to not touch the x-axis?
33.
No.
100.
But you have the correct idea, but it's just not going to be 33.
1. Greater than 0.
32.
Boy, can you explain why it's 30? Your first answer and why it's the answer is k is greater than 32?
Because it sits on the x-axis, so you have to go above the x-axis, which is anything greater than 32.
Excellent. Okay, so does everyone notice down here, the y value at the bottom at this point is negative 32, right? So if I add, so notice here, this is k is being added at the end. If I add 32, that means my graph moves up 32 units, which means it will look like,
That's so incredible. It'll be like,
it will move the whole graph up, and basically it means that at this, it will touch here, and then it goes up to this guy, and then like that, right? So if k is greater than 32, it won't touch the x-axis at all. Yeah, we seeing that? Excellent. So for this last one, the last two questions, if you see a question which is a one marker like that, which like comes off of all these other questions, notice here, like we did all this hard work in parts 1 and 2 to actually draw the graph. Does everyone see that? Irvin. First two parts, we did all this hard work in getting to like sketching a curve. Parts 3 and 4, we're just kind of reading information off that graph. Where do you see it increasing? How do we make it so that it has no solutions? And so here, we're just using the stuff that we did in the first 3 parts to actually get us to last 2. Everyone cool with those 2 answers? No solutions just means, so if you, let me just draw a couple of quadratics to actually show you this. So, yeah, so as in, so first one, let's just draw a couple quadratics because this quadratic, how many solutions does this quadratic have? 2 solutions because it touches the x-axis at these 2 points. How about this quadratic here? It touched once, which means it has 1 solution. Now, realistically, it means you have a double solution at that point, but let's not talk about that. How about this last one? 0 solutions. We want it to have no solutions, which means it has to be above the x-axis. Yeah? Okay, cool. Let's move on. Flip the page to 18. And here, we're going to start talking about what the relationship is between original function f(x), the first derivative f dash x, and the second derivative f double dash x. So here we have a table, and I think it's missing a few rows. Now, I'm not sure if I'm doing this correctly, but we're just going to do it anyway. Okay. So, what we're doing here is we're trying to identifying what do these points look like on a graph of f of x. So, a 0 crossing on f of x is a x-intercept. Okay, so if I have a 0 crossing on my original function f of x, that means that I have an x-intercept. Now if I have a 0 crossing on my f dash x, so if I have f dash x is equal to 0, what does that mean for my original function? What does that look like? Stationary point. So here, this is a stationary point. That's a stationary point. What happens if I have a 0 crossing on my second derivative, f double dash x? No. Just get rid of the h. This is a POI, a point of inflection. Point of inflection. But it's a question mark, because if you remember, what we need to do is check that on either side of my point of inflection, it has different signs. Okay. Now, next one. If I have a turning point, I'm going to just actually, we're only going to like start looking at these 2 parts in a moment. If I have a turning point, what does that mean for my yeah, it's a what's it called? F dash x is equal to 0 here. If there's a turning point on my original function, that means that in my first derivative graph I have an x-intercept. Shh, guys. Just want to fill this in, and then we're going to actually go through these few examples, and hopefully it'll make more sense. We're just going to fill in these next parts. I'm just going to actually fill it in because I'd rather just get to the examples. And if there's further questions, you can ask. Turning point and f dash x is equal to 0. Okay. Can you just fill that in for me? And we're going to go through a few examples.
Would that also be the x-intercept?
No.
I only speak the truth.
These are just... Okay. Now, we're going to go through an example. Shh. What we're basically doing here... Guys, year 12s. Mariam. TJ. Shh. So you copy this down, and then we're going to go through. What we basically want to do here... Shh, guys. Year 12s. Can we get through this, please? Because it is not applicable, I think. I'll need to check up on that for you. Now, what we want to actually do here is be able to draw what the graphs of subsequent derivatives will look like on the same graph. So we're going to go through an example of this. I'd rather just get to the examples than necessarily go through the laws and results. So, we'll move to this example. This diagram shows a function f of x. Sketch its derivative.
You want to answer it?
No, just hang on, please.
Same color and then just like one number.
Okay.
What if it should look?
Okay. Here is an original function, f of x. What we want to draw is the derivative on the same set of axes. Now, when I'm looking at these types of graphs, if this is the original function, there's a few things that I'm actually looking for. What does this first derivative tell me about the original function? This is our what? This tells me my gradient. So what I'm looking for is the gradient of my function f of x here. Now, the first things I'm looking for actually is when the gradient is equal to 0. When is the gradient equal to 0 on this particular graph? Across the x-axis? No. The turning point. Excellent. So at this point here and this point here, notice the gradients at these 2 points are 0. So first derivative here is equal to 0 and first derivative here is equal to 0. Because these are our turning points, they're stationary points. So here, your gradient, notice, is 0. And same thing here. The gradient here is 0. Everyone cool with that? Is everyone cool with that? Okay. Now, shh. If that is my... If those are my stationary points, what does that mean for my first derivative? At those 2 points, my derivative is equal to 0. What does equal to 0 mean on a graph?
That's a state.
No. It's a solution. What do solutions look like, TJ, on a graph? X and intercept. So here, Mariam, you're not. Here, these 2 points, which are my turning points, my stationary points, as TJ said, they are solutions of f dash x is equal to 0, which means on my first derivative graph, they're my x-intercepts. At these points, these are my x-intercepts of my first derivative graph. Does that make sense? Yeah. On my first derivative graph, these are my x-intercepts. Okay, now that I've done that, I'm going to look at the bits left and right of these parts. So here, I'm going to look at this section here, and then this final section here. First section in the yellow. Can someone tell me, what do we know about the gradient at that point in that section? It's increasing, which means that the first derivative is positive. It's greater than 0. On my graph, that just means it is above the x-axis. So in this part, here, it is above the x-axis.
Why is it going down?
Because we're reaching to that what's it called? We're reaching that stationary point. Stationary point means the gradient is 0. And notice here, look at the gradient as we get closer and closer to that turning point. What happens to the gradient? Here, the gradient, the lower we are away, the gradient's really steep, right? And what happens? It becomes less steep, so it means it's getting closer and closer to what value? 0. Which is why the gradient, if you notice the blue part, it's really positive up here. And it becomes less positive, less positive, less positive, less positive until it gets to 0. So this first section, the gradient is positive because here this is increasing. What about the green section? It's decreasing. It's decreasing. So here it's going to be negative. Now in particular, there's also one point I probably want to look for in here. What's that point called?
The
Point of inflection. There's this point in between where it's a point of inflection. Where it suddenly goes from concave here, in this case it would be concave down, to suddenly being concave up. Does everyone see that? Yeah. On my first derivative graph, that refers to a turning point. So here, I have a turning point here, and it goes back up to my...
what about your y-intercept? The y-intercept.
So you're not too fussed about the y-intercept for these questions here. You're just trying to draw a sketch of what the first derivative would look like.
Okay.
These ones you're not too fussed about the y-intercept.
Why don't you go through the actual point?
What about...
Because as in, you don't necessarily go through the exact point. Because that is like our original function. We're just trying to draw like what the shape would look like. Yes?
What about the top, intersects the other graph?
So the intersections of the other graphs, don't worry too much about that. Here we're just trying to sketch what the derivative should look like. If you get you're just trying to get the shape of the derivative. That's what you were going for.
And then it increases.
And then it goes back, well, it's not increasing. Notice, oh, actually, it is increasing eventually. But notice here, this whole section in the green, it's decreasing, right? Yeah. Notice all my values on my derivative, they are still all below the y-axis. The x-axis, I mean. This whole section here, it's below the x-axis. Does everyone see that? Which is why it's decreasing. If the first derivative is less than 0, which is what below the x-axis means, it is decreasing, which is what the original graph had. Okay, what happens on the right of that second turning point on my original function? It goes positive. So we go back up. So it kind of looks like parabola. Excellent. The yellow bit's increasing. Well, have a look at the shape of it. It's going from bottom left to top right. It's increasing. So it's going...
Does it have anything to do with concavity?
So, not really. But like, if you want to think of it in terms of concavity, like one side of your concavity will go up, one side will go down. Once you have a turning, if you have a turning point.
Even if it's like this, it goes down.
It's like you're walking uphill and then you walk down.
Yeah. So you can think of it in that way. Like uphill is increasing, downhill is decreasing. That's a nice way of thinking of it.
But it's concave down.
It's concave down the whole time. Correct. So this whole section here, so let me do it in yellow. This whole section here is concave what? Down. And this whole section here is concave. That doesn't have anything to, that doesn't really affect my graph. The only point that does is this point here, because notice this point here, which is the point of inflection, where it swaps from different concavities, it's my turning point of my first derivative.
You could say that the more down a car goes a hill, the more speed increases because the derivative is
so you can, if you can think of it that way. So like the more sharp the way you can think of it is the sharper the gradient is. So here TJ's made a point that at this point here, this is like the sharpest point, or like sharpest speed, right? That is the lowest y value you're going to get for your first derivative, because that's the quickest it's going downhill. When you get close to your turning points on your on the original graph, what's the velocity at those turning points? Close to zero, which is why on my derivative they're very close to the x-axis. we're getting closer and closer to 0, because those are the points where the speed is getting closer to 0. Is that cool with everyone, this first example? Okay. If you're cool with that example, can you please flip to the next page, so page 19, and this one we're working actually backwards. So this is when we've got the original function and we want to draw the derivative graph. Now what we got in the next part, in the 1999 HSC question 8, we've got a graph of the derivative. So here, this is a graph of the gradient function. So here they've given us f dash x. What we want to do is figure out for what value does x have a local minimum and justify your answer. So let's talk about local minimum. Local minimum. What's the conditions for a local minimum? Down and then up. So first of all, is a local minimum a stationary point? What does it mean for it to be a stationary point? F dash x needs to be equal to 0. Okay, so let's start off with that fact. If this is my f dash x graph, so this is my first derivative graph, where do I have f dash x is equal to 0? 1 and 5. Those are my two x-intercepts. So this is my first piece of information. I've got f dash x is equal to 0. Let me do that in another color, and then I'll highlight it. Here, and I've got my 2 points where it's equal to 0. Then Mariam said the really important point. So for it to be a local minimum, on one side we need to have, so f dash x, oh hang on, if we draw up a table. So let's say we have a random point. On the left of my point, what do I need my first derivative to be equal to if it's a local minimum? Negative, yeah, because we need to go down, and then on the right hand side it needs to be positive. It needs to go up. So on the left hand side of my point, it needs to be negative, and on the right hand side of my point, it needs to be positive. Yes? A. I just picked a random letter.
Oh, why is it 9 then?
Okay, so if you have a look at my graph now, so my first piece of information was local minimum means it's a stationary point. So I looked for my my zeros, x-intercepts. Then from there, I'm going to use my fact that a local minimum is down and then up. So let's have a look at this first one here. At x is equal to 1, on the left-hand side of x is equal to 1, is it positive or negative?
Negative.
Hang on, think about it. This is my first derivative graph. It's positive. Because of my first derivative graph, I'm just looking for if it's above the x-axis or below the x-axis. And on the right-hand side, is it positive or negative? Negative, because it's below the x-axis. So what do we know about this point here? X is equal to 1 is a, if it's positive, local max, because it's a positive, so it goes up, and then it's a negative, so it goes down. So 1 is a local max. How about 5? What, on the left-hand side of 5, what do we have? It's negative, and it goes, which means it's going negative, so it's down, and then up. So this is a local minimum. So here we have, so x is equal to 5 is our local minimum, because when x is less than 5, the first derivative is less than 0, and when x is greater than 5, it is greater than 0, which is this down and up motion that we need for our, for local minimum. Does that make sense? Do I need to go through this again? Does it actually make sense, or are people just nodding? Yes.
I didn't get that thing that you wrote.
The bit thing that I wrote? Okay. So here I wrote x is equal to 5 is our local minimum, and I had to justify, right? So when x is less than 5, so the part to the left, the first derivative is less than 0. Are you cool with that? Which means it's going down. And on the right-hand side, when x is greater than 5, the first derivative is greater than 0. Notice here, it's greater than 0. Whoop. It's greater than 0, which means it's going up. So this is what makes it our local minimum. Are you cool with that?
Got it.
Got it? Excellent. Any additional questions? Okay. I'm going to get started on the first two parts of the next question and we'll finish it next lesson.
Wait, so can you write that down?
You can write that down. Bell's going in 3 minutes. And my...
Does anyone know what's we're back?
I have duty somewhere today, don't I? That's my account. Okay, let's just answer the first two questions. What happens to for what values of x is derivative negative? Derivative negative means that on my original function it is. What does f dash x being negative mean? It's decreasing. So when is your graph decreasing? Yeah, excellent. So this first part is just between -1 and 3, because notice here, this part, it is decreasing. It's going downwards. Okay, next part. What happens to f dash x for large values of x? So if you have a look, we're looking for large values of x, so we're going towards this side here. What do you notice about the graph as we get further and further along the x-axis? What happens to the derivative? It's asymptote. What's a gradient looking like? Goes to 0. Excellent. It goes to almost stationary. So here, when x goes to infinity or big value, the first derivative goes towards 0. Because it's getting, as you notice, it's becoming flatter and flatter and flatter and flatter. We're getting to like the top of the hill, which means once we hit the top of the hill, it's stationary. Nothing there. Nothing to continue walking. Next lesson, we'll have a go at drawing the gradient. I'll give you a second just to copy that down, and then you can go.